The method we're going to present here is called the backward-Euler method. And it's actually a numerical method in order to solve first-order ordinary differential equation. Very similar to the forward-Euler method, but it has some subtle differences that makes the method itself very different from the other, with different characteristics. Okay, again, here we have the first order ordinary differential equation that we want to solve. It has the equation itself and the initial condition. And here, in this method, we're also going to use the linear approximation for the Taylor expansion evaluated at time t as well. But in this case, we are going to do so in order to get the value of the y function at time t minus delta t. So we are going back on time somehow, so that in this case our time interval is going to be minus delta t. So, and that's important. This sign is going to be important in order to apply, in order to consider the Taylor expansion. So if we just apply directly the definition of the Taylor expansion, we do have that the wave function evaluated at time t minus delta t, it's equal to the wave function evaluated at time t minus, because in this case the time interval is negative, as we said before, that this minus is coming from this negative time interval, the derivative of the function with respect to time evaluated at time t and times delta t. And as in this case, we do have the derivative of y with respect to t can be this function f, which depends on t and the y function. We can write this Taylor expansion in this way. Okay, this is the Taylor expansion we do have in order to get the I evaluated at time t minus delta t. And again, in the time variable, we are defining a mesh. So we are going to apply this Taylor expansion here for when time t corresponds in this case to the time ti plus 1, so that the time t minus delta t would be the time ti. So making these substitutions in this Taylor expansion we have just derived, we can easily get this equation here. The I function evaluated at time ti is equal to the y function evaluated at time I plus 1 minus this f function, which is evaluated at time I plus 1 and can also depend on the y function evaluated at time I plus 1 times delta t. And again, our aim, of course, it's actually going to be the same. Once we know the values of some of the y function evaluated at some point, we want to go to the next time step. That's why, in order to have that, we're going to pass this one to the left, and this term we're going to pass it to the right, and this is the expression that we do have for this method. So, which basically is the following. Again, as we had before, as we had in the forward Euler method, the wave function evaluated at time I plus 1 is equal to the wave function evaluated at time I plus the f function, which is the derivative of the wave function, but in this case it's evaluated at time I plus 1, so that it can also depend on the y function evaluated at time I plus 1. As you can see here, we have that the y function evaluated at time I plus 1, it can also depend on the y function evaluated at time I plus 1. So that's why this method is called an implicit method, because in order to apply definitely that method, we need to do some we need to work probably that we need to work more on that expression here, because in order to apply that will need to clear from the whole expression here an expression for a definite expression for the y function evaluated at time I plus 1, considering that dependency on y evaluated at time I plus 1 as well. And it's important, I think, as we also did for the forward Euler method, it may be important to have like a geometrical description of the method in order to have a deeper analysis, a deeper understanding of the method itself. And that's what we're going to do next. Again, here, that's the method itself. Okay, so as you can see here, the value of the y function evaluated at time I plus 1 has two different contributions. This is one, and we also have, and this is the second one. Okay, and as happened in the first term is actually the same one as we had, the one we had for the forward Euler method. And again, here the aim is more the same. Basically, the aim is, once we know which is the value of the I function at time I, we want to have what's going to be the I function evaluated at time I plus 1. And considering that method, we have two different contributions. One is this one, which basically the first contribution is like this one. It's the y function evaluated at time I, but we have another one. And for that, let's consider that this is like the f function here. And we know which is the f function evaluated at time I. But in this case, in the second term here, as you can see, we are using the derivative. This is the derivative, but in this case, the derivative, it's evaluated not at time I, but at time I plus 1. So we are using the information on the derivative at time I plus 1. And remember that the geometric interpretation of the derivative was the tangent of the angle that is formed by the geometrical tangent and to the function at this point, and the positive direction of the axis, which in this case is this angle here. This is actually the geometrical tangent, and this is the angle which is formed by the geometrical tangent and the positive direction of the time axis. So actually this f here, f function evaluated at time I plus 1 and I plus 1, is actually a tangent of beta. This is the geometric interpretation of the derivative. In order to apply it to here, we're going to translate, to make a parallel translation of this geometrical tangent to the left, to put it just, over on the time t1. This is the geometrical, this is translation. Okay, these two are parallel, so we do have the same angle here. And again, this function here, which is the tangent of beta, which is this beta being this angle times delta t, with delta t is this one, delta t is the time interval times delta t, is actually all this side we do have in this triangle here. This is tangent beta, or the f function times delta t. So that would be this orange line, orange side, would be the second contribution here. The first one is this one, and the second one is this one. So summing the two, we are getting the result for the y function evaluated at time I plus 1, considering that backward Euler method. Of course, it's not going to be exactly the same as the one we do have for the exact one, because we do have some error here, error, which in this case, as it corresponds to the forward Euler method, the error goes to the like the square of the time interval, and that will correspond to this distance here. So that would be like a geometric interpretation of this backward Euler method. And the interesting thing here, especially when it's compared with the forward Euler method, is that in this method we are using the information on the derivative, which is this one here, on the point where we are going to evaluate the I function. So we're using information on the derivative of the point that we are going to evaluate. While in the forward Euler method, all the information was just based on the previous point, on the point at time I. So somehow here we are using the information on the point that we want to evaluate. So that's the main difference between forward and backward method. Even though the basics actually and the tools you are using are actually the same, actually the error of the method is the same. The philosophy is somehow quite different between the two.